graph is continuous. Graphically, graphically a function is continuous at a point if a graph does not come apart at that point. Does everybody understand what come apart means? It means there's no hole there, there's no gap there, there's no jump there, okay? That we could still, at any given point, we could still run our pencil across it and never have to lift it up. That's what it means for it to be continuous. All right? We'll learn to define a function to be continuous at a if the limit, and y'all need to understand what this means, the limit of the function as x approaches a, this is from the left and from the right, is equal to f of a. Now, why do we say that? Because there's a couple different options that we can see. And this is where we get into discontinuities. When is it not? Sometimes it's easier to tell when it's not continuous than it is when it is continuous. So if it's continuous, let's look at this function right here. This function is continuous. You know how I know this function is continuous? Guess what? I never picked my pencil up, did I? Drew the whole thing at once. Now, how do we tell it's continuous at a? This is f of a, isn't it? That point right there, would you agree? The y value is f of a. So this point right here is a f of a. Now, I need you to understand what it means when I say, as we approach a from this side and we approach a from this side, are we approaching the same value of y? In other words, as we approach from this side, we are getting this closer to the y value that way, aren't we? As we approach a this way, then we are getting closer to y here as well, aren't we? So as we zoom in this way, we are zooming in on the y value, the same y value this way. Now, the other piece is that not only do we have to zoom in this way, but at this a, we get that point that's just in between. In other words, it zooms into the point where it's actually equal there as well. Does that make sense? So as we get closer and closer and closer to a here, we get closer and closer and closer and then are at f of a here. Okay? Yes? No? I lost you? I hope the visual helped. So that's what this means. So as we close in, on a, from the left and the right, we close in on the same y value, which would be f of a up and down. Okay? And then at a, it's equal to f of a. Now, what is a removable discontinuity? Also called a point discontinuity. This is called a point discontinuity. That looks like this. As the function's going this way, at a, all of a sudden we have this gap, this hole. So what's the difference between the first one and the second one? I want you to take a look. As we're closing in from a this way, we are closing in on the y value, this same y value this way, aren't we? The difference is that at a, it doesn't equal that y value, does it? You see what I'm saying? It did here. It was closed up here. Here, if I were to try to draw this, I would have to draw it to here, pick up my pencil to the other side of that and keep going. So this hole, removable discontinuity or point discontinuity, often this is called a hole. If there is a hole present right there where we're taking the limit, it is not continuous. Yes? Okay. So the difference between the first one and the second one is that there is a hole here. In other words, A does not lead to f of a. In other words, at f of a, the function is undefined. Now, how do we get that? How do we know we have a removable discontinuity? We have some x factor in the function that cancels away. For example, this would be an example of one. For example, if we had f of x equal to x plus 1 over x plus 1 times x. Look what will happen here. That factor cancels out 1 over x. There is a hole right here. In other words, that x equals -1. If we set that factor equal to 0, we can tell where there will be a hole. Does that make sense to everybody? So a factor of the function cancels, right? Or is removed. Has to be a factor with an x in it. Can't just be like, oh, I got rid of 2 in the top and 2 in the bottom. That doesn't make a whole. It's when there is an x that's removed, okay? From both top and bottom. So is everybody clear about that? It produces a hole at that point, that x value. All right. Next type is a jump discontinuity. A jump discontinuity looks like this. What do we notice right here? It jumps, doesn't it? Now what we know is one function jumps to another function. As a matter of fact, we know this is a piecewise function, isn't it? Notice I'm saying often do this. They don't always do this. Piecewise functions, kids make a mistake in precal and get piecewise in their head and go, oh, well, it's piecewise, therefore it must automatically be discontinuous at that point. Not necessarily. You can have a piecewise function that is continuous. Do you want to see what that looks like? A piecewise function that's continuous, all we have to have, and I'll erase this so you don't have to, is what if it did this, and then it went like that. This function is different than this function is. Do you get it? But they are still continuous at that point. So be careful. You have to check at the point of discontinuity and see that you're testing and see, is it the same value there? Okay, so we test here. We test both functions at A to see if they match. If they do, it does not have a jump continuity. If they don't match it, it does have a discontinuity. One of them goes to 4, the other one goes to -2. Get it? Good? No, maybe, sort of. Okay, so all right, so here we go. And we call it a jump discontinuity because it jumps. Infinite discontinuity. Infinite discontinuity is when we have a vertical asymptote. Okay? If we have a vertical asymptote here, everybody remembers what a vertical asymptote is from Algebra 2? If it has an infinite discontinuity, there is a break at A. Vertical asymptote at x equals A. And why we call it infinite is because if we have a vertical asymptote, remember what it does. Do you remember what the function does at a vertical asymptote? It either goes to infinity or to negative infinity. Now there's options. They can both go this way, they can both go this way, or they can go opposite directions, this way or this way, can't they? Any of those are still infinite discontinuities, okay? They're still infinite discontinuities. So let's just do this one. So this goes to negative infinity, and then we'll make this side go to positive infinity. So this has an infinite discontinuity. These are rational functions. Often rational functions have infinite discontinuities. Does everybody know what the word rational means? Fractional, like we have an x in the numerator and an x in the denominator, or at least an x in the denominator. That's a rational function. Rational means fraction. Okay? So, it says, identify the points of discontinuity and describe the types of discontinuities. All right, so anytime we have an x in the denominator, we have to check and see if we have a vertical asymptote. Guess what? We're going to. Okay? So here's how we check. We're going to factor. So first we're going to factor if we can. Did any factors cancel? If they did, then guess what? We have a whole and a point discontinuity. Okay? So this would be our point discontinuity. Second, any factors left in the denominator? Set them equal to 0 and solve for infinite discontinuities. Does everybody understand what I mean when I say VA? What does VA stand for? Vertical asymptote. VA. I'm going to use abbreviations because nobody wants to write vertical asymptote over and over again, do they? So is it okay if I use VA for vertical asymptote? We all good? Okay, so you'll see it in your notes. Should be fine. All right, so if that doesn't work, now the only other kind we had was what? Jump. So for jump, once we check those, we're going to third and we're going to see, is it piecewise? And we'll know it's a piecewise function because it'll have two separate functions. This one will be for jump. Okay, check if they're transitions, and I'll show you what that means because we'll have an example there. All right, so let's go through this. So this is kind of how you can check for each type. So first things first, can we factor anything out here? And if you say X, I'm going to get paper wads and start throwing them at people. I'm kidding. Does everybody understand you cannot do this? If you can't pull it out of everything, you can't pull it out of anything. You cannot do that. That's a no-no. No. So is there any factors I can get rid of in those? No. So is there going to be a whole? No. So then we go on to step 2. Is there anything left in the denominator that has an X? There is, isn't there? So what did it say to do? Take whatever's left and set it equal to what? 0. So we're going to take this as X minus 3 and set it equal to 0. What do we get? X equals what? 3. So we have a VA there. So what type of discontinuity would that be? Yes. So we have an infinite discontinuity. Okay? Seem easy enough? Is this piecewise? It's just one function, isn't it? Did I care about the numerator? No. Just checking the denominator. All right. So any questions? Are we good? Just infinite. So let's do this guy. Can we factor this? What will it factor into? What will the numerator factor into? Difference of two squares. So, yep, x plus 2 and, oh, so we factored. Can we eliminate a factor? Yes? X minus 2 goes away. So we have a factor that was eliminated, so what type of discontinuity do we have? A removable, don't we? Or a hole. So we know there's going to be a hole there. So this means there is a removable. Or point discontinuity. Now we got to figure out where it's at. So we're going to take that at, set it equal to 0 again. Okay, to figure out where it's at, so at x equals what? So at x equals 2. Now, so we just take the factor that we eliminated and set it equal to 0. Okay? Yes, sir. No. We're taking this to figure out where the discontinuity is, where the hole is. Good question. I think there were some other people who were like, what? The only time we ever set anything equal to 0 is either if it's in the denominator and we're trying to figure out where the vertical asymptote is, or if it's a hole and we're trying to figure out where the hole is, okay? Never set anything for now with discontinuities. We don't set anything from the numerator equal to 0. So now, step 2 says, do we have anything left in the denominator after that went away? No. So do we have any infinite discontinuities? No. Is there more than one function? No. So do we have any jump discontinuities? So the only one we have, so we've ticked off through our list, so the only thing we have is a hole at x equals 2. Okay. So let's move on to a couple more and then move on from this. All right. When would we have, I don't feel like there's enough examples here. Let me give you one more just to look at. You don't have to write this down, but one more just to look at. And let me see if I can get you a good one. Hang on. What if I had this? F of x equals... Now, you ought to be able to jump to the only kind that we can actually really see if we have one. What type of function is this? It's piecewise, isn't it? We have one function and we have another function. Now, when I said check at the boundaries, you know what the boundary is? This number right here is our boundary. This is where it changes, isn't it? So we have to check f of 2. So we have to check this. F of 2 is going to be, this is a constant function, isn't it? So no matter what you plug in for x, what's the y value going to be? Really? 1? It says the function is 1, no matter what x is, right? The function is 1. So at f of 2, this is 1. Now we check this guy. F of 2 would be 2 plus 3, which would be what? 5. Do you see that these do not match? If they don't match, guess what type of discontinuity we have? It jumps from 1 to what? 5, doesn't it? At 2, it jumps from 1 to 5. So we have a jump discontinuity here. At x equals 2. Do you see how you tell whether or not you have a jump discontinuity? You'll know when to use it because it'll have more than one function. You just have to check it, each one of those boundaries. Okay? All right. So let's talk asymptotes. Asymptotes. We have two different types we look at in this class, vertical and horizontal. We already know how to find vertical ones, don't we? How do we find vertical asymptotes? What was our test? If we had factors in the denominator that don't disappear, then we set those equal to 0 and solve, and those are our vertical asymptotes, okay? So vertical asymptotes, let's do those in, let's do those in gray. So they have a vertical asymptote, not in gray. Let's do these in blue. So vertical asymptote would be here or here, correct? And a horizontal asymptote would be here. There's my horizontal asymptotes. Okay? Now, for a vertical asymptote, and then we'll deal with what the rest of this means. For a vertical asymptote, boom, what do we need to know? X equals C. The graph of the behavior will approach the vertical line and either increase or decrease without bound. It never intersects a vertical asymptote. So the limit, as it approaches this guy right here, I want you to look at this notation. As it approaches, one side approaches what? And the other one is going to approach, or it could go, both of them could go down, or both of them could go up, or one side could go up and the other side could go down. But either way, it's still all either positive or negative infinity, isn't it? So the limit from the left is going to either be positive or negative infinity. And limit from the right is going to be either positive or negative infinity. In other words, for this picture right here, where is that vertical asymptote at? Where is it at right here? 3. So this vertical asymptote is x equals 3. That is my VA. So the limit, we would write that as the limit of f of x as x approaches 3 from the left. Notice I put a minus sign after the 3, not before the 3. After the 3, up at the top means from the left. How is it approaching from the left? So from the left side, where is this function going? So negative infinity. So we would put negative infinity there. Okay? And then the limit of this function f of x as x approaches 3 from the right. That's why we put a plus sign after it. That means from the right. Where does this guy approach? As it's coming in from the right, it's going where? Positive infinity. So that would be the limit. Okay? Now, horizontal asymptotes. Horizontal asymptotes are y equals b. That's how we're written. So we got to figure out where this guy is. Where is this horizontal asymptote right here? Where does it intersect the y-axis? Where does that intersect the y-axis? Y equals what? 1, right? Okay, so at y equals 1, so the graph is going to tend towards this, whatever this b is, where it crosses. Along that line. Notice something. It is possible for something to cross the horizontal asymptote. Guys, we're talking end behavior here. It does not matter what this thing does in the middle here. It can cross back and forth over this horizontal asymptote as much as possible. When we're looking at the horizontal asymptote, we're looking at what is it doing only really far to the left and really far to the right. It cannot cross it out here to the left. It cannot cross it out here to the right. So the limit out here to the left is getting closer and closer and closer and closer to this value, isn't it? So the limit is getting closer. We're looking up and down on this one. So the limit of this guy, as it goes to the left, is going to be at 1, isn't it? And the limit of this guy, the y value, is going to go down, 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 down on this side until it gets closer and closer to 1 on this side as well. So for vertical asymptotes, we're saying what value is happening as we go in this way. For the horizontal asymptotes, we're asking what's happening as we're coming in this way. Okay? All right. So the limit, and we always use the same notation. As x approaches negative infinity, I know. I'm sorry. I got it. I got it.
Thanks.
Mm-hmm. Can't help it if I like this. Keep going. You pushing? So we're only missing Cameron today. No, yes. All right. Let's keep trucking. We got lots to do still. All right. So the limit as x approaches negative infinity. This is asking you what is it doing as it goes to the negative infinity would be to the left, right? And positive infinity would be as it goes right. And you always use this does not change and this does not change. What changes is what you put here. That is either going to be positive infinity, negative infinity, or some number. So what is the number for this guy? What's happening here? It's getting closer and closer and closer to 1, isn't it? And on this side, it's also getting closer and closer and closer to 1. So for both of these, we would put 1. All right? Now, is it always going to be the same number? No, it's not. You'll have to look at the graph. Okay? Slant asymptote. A slant asymptote means that it goes sideways. I want you to look at something. Do you see this guy right here? Oblique asymptote would be this guy right here. It is a dashed, slanted line. That's why it's called a slant asymptote. This is an oblique or slant asymptote. Okay? Slant asymptote. Now, a slant asymptote, notice what happens here. As it gets to the end, as it goes to the right, as this function goes further to the right, what's happening here? What is its limit? Yeah, say it. I saw you mouth it. Where is it going? To the right, where's this function going? Infinity. Now, as we go to the left, where is this function going? Negative infinity. Did I look at it here or did I look at it here? No, I did not look at it in the middle. I only looked at it on the ends. Horizontal asymptotes are end behavior. Nothing in the middle gets paid attention to, only to the far right and to the far left. Get it? So we are only looking over here and over here. So let's write these. We write these the exact same way every single time. The limit of the function f of x as x goes to the left, it goes towards negative infinity, and the limit of f of x as x goes to the right, which would be positive infinity. And then we fill in those blanks. So look at that graph. To the left, what is this guy doing? To the left, what is this guy doing? Where's it going? So that's what goes here. Are you seeing it now? Goes to negative infinity. To the right, that's what this means, positive infinity. To the right, what is this guy doing? It's going to infinity. End behavior is easy, guys, if you've got the graph. Super simple. You just look at the graph and see what's it doing on the ends. Is it tabling out? If it tables out flat, then that's a number. If it doesn't table out flat, if it does something like this, then that's infinity or negative infinity. That's really the only options you have. Finding a horizontal asymptote. Case 1. If the numerator degree, does everybody understand what degree means? It is the highest variable power. So if the highest power in the numerator is less than the highest power in the denominator, write that down if you need to, then y equals 0 is the horizontal asymptote. Let me give you an example of that. Bottom is bigger than top. So y equals x minus 2 over x squared minus 6x plus 9. Do you understand the degree? What degree is this guy? He's to the first, isn't he? That's the highest power. This is the highest power here. Does everybody understand now when I say the bottom power is bigger than the top power? This is bigger. So the horizontal asymptote is y equals 0 every single time. Now what happens if they are equal degree? Bottom equals top. Then the ratio of the leading coefficients is the horizontal asymptote. In other words, y equals a over b. Now let me show you what we mean by that. Y equals 5 minus 8x squared over 2x squared plus 3x minus 4. So I'm going to highlight what are the lead terms here. What is the highest term on this side? Highest variable, power, minus 8x squared, right? So minus 8x squared here. And what's the highest one on the bottom? 2x squared. Do you notice that those are equal? Those are equal. So what we do is we peel off, this is our A, and this is our B. Does that make sense? So the horizontal asymptote is y equals a over b. So my a would be negative 8 and my b would be 2, wouldn't it? So my horizontal asymptote would be at negative 4. Do you see that? If the powers are the same, strip off the numbers in front of them and make them a fraction and reduce it. Last but not least, what happens if the numerator is bigger than top bigger? So we did the top smaller, the bottom's bigger, we did their equal, now we're doing the top is bigger than the bottom. The graph has no horizontal asymptote. For example, that's when it maybe has a slant asymptote, but we'll get to those later. Y equals x squared minus 5x plus 4 over x minus 2. What do you notice here? What is the lead? What is the highest power in the top? What is the highest power in the bottom? X, and that would be x to the first, wouldn't it? Which one's bigger? Top is bigger. So this is an example when the top is bigger, there's no Horizontal asymptote. So let's figure these out. We can do these pretty quickly and then actually tell what they are. So here we go. Take a look at A. Compare. Is the top bigger, smaller, or are they equal? Okay, so we're only looking at the lead coefficients. We know the powers are equal. So I have a what? I have a horizontal asymptote. What's the coefficient in front of the x? 1, right? So it would be 1 over what? 3. Okay? Are we good with that? It also said find the vertical asymptotes. To find the vertical asymptote, remember what we do? We take this and set it equal to 0. So we're going to take 3x minus 6 and set it equal to 0. And solve for x. 3x equals 6, so x equals what? 2. So we have a horizontal asymptote at y equals 1/3 and a vertical asymptote at x equals 2. Okay? Let's try another one. And we have to ask if we can factor or not. Can we factor this one? No. So let's look at these first. Lead coefficients, which is bigger? Top, bottom, or are they equal? Bottom bigger. So we have a horizontal asymptote at y equals what? Yeah. It's automatically y equals 0, isn't it? If the bottom is bigger, it's y equals 0. Now, we need to find vertical asymptotes. We take the denominator and set it equal to what? 0. X squared minus 9 equals 0. So x squared equals what? 9. I'm going to add 9 to both sides. And now how do I get rid of the square? Square root it. So I get x equals what? Not just 3. What do we always have to? We do the square rooting and we're solving. What do we have to put in front of the answer? Plus or minus. So plus or minus 3. So we have vertical asymptotes at x equals 3 and x equals -3. Okay? Look at another one. How are we doing so far? Are you getting this? Ooh. Now guess what we need to do? We need to factor. Don't we? They're both factorable. What will the top factor into? Difference of two squares, guys. X plus 4 and what? X minus 4. Okay. The bottom, the denominator will factor into what? Okay. Now, that's completely factored, isn't it? Now, here's the cool thing. What did we notice? That went away, didn't it? So what type of discontinuity do we have? Let's start there. If we have a factor that eliminates, what type of discontinuity do we have? We have a hole. Yeah, removable, don't we? It didn't ask us that, but it's good to remember. So now we got to do horizontal asymptotes. HA. Now for horizontal asymptotes, we can look back at the original. All right? Let's look back at the original. What do we need to compare? What to what? Top to bottom. So which two terms are we circling? X squared and x squared. They are what? Same. So this is going to be y equals what? What's the coefficient in front of the x squared, and what's the coefficient in front of the x squared? 1 and, so 1 over 1, which is what? 1. So y equals 1. Now, for the vertical asymptotes, I had to factor because one of my factors went away, guys. If one of my factors goes away, then the reason we don't have to set this equal to 0, because it disappeared, didn't it? What's the only one we have to set equal to 0? The one that's left. So to find our vertical asymptote, we set whatever's in the denominator that's not gone away equal to 0. So x plus 7 equals 0. So what is my vertical asymptote? X equals negative 7. Okay? Good to go. Last example. Can I factor anything here? Anybody want to mark out x squareds? No. This has an x squared, this has an x squared, this does not have an x squared. You cannot mark it out, so we cannot factor, can we? So, I want you to find the horizontal asymptote. There is one. Figure out what it is. Then we're going to go to end behavior and rate of change. And comparing graphs. We're going to hurry through the rest of this. There's a lot today, isn't there? Yes, I have a bucket of liquid. Like lifting weights and hydrating all at the same time. I'm sorry. I don't know why my phone is thinking. Okay. Turn it off so we don't have to listen to it. Binging. Not fair for me to listen to mine binging when you can't listen to yours binging. I'm all about some being fair. Ah, there it is. All right. So we circled this, right? They are the same. So y equals what? Yeah. 3 over 2. You got it. Now, vertical asymptote. What do I do to find the vertical asymptote? Take what's in the where? What's in the denominator and set it equal to? Okay. Now solve that, if you can. We get 2x squared equals what? Negative 1. And then x squared equals negative 1/2. And then things come to a crashing halt because why? What do I have to do? I had to take the square root. Uh-oh. Why is this a party foul? Yeah, you can't take the square root of a negative number, can you? This is negative, so we can't do that. So is there a vertical asymptote? None. And make yourself a note of why I marked that out if you don't remember. You can't take the square root of a negative. All right. So do you feel like you can find those? End behavior. How do we do end behavior? Guys, this end behavior tells you one thing. There's one thing you need to know. The end behavior is either going to be positive infinity, negative infinity, or go to a specific number, isn't it? Usually if it's a polynomial function, it's going to go to positive infinity or negative infinity. How can we tell? We can tell from using two things. What's the highest power? If the highest power is even, if the highest power is even, both ends go the same direction, don't they? Highest power is even, we're either going to have the coefficient is positive, and the function's going to look like this. If the leading coefficient is negative, then it's going to look like this. And we can tell what the end behavior is from that. Do you get it? So let's take a look at an example of this. This would be the limit of f of x as x approaches positive or negative infinity is going to go to, they're both going up, so what is the limit going to be? Positive infinity, isn't it? This one's going to be exactly the opposite. This guy, if both ends are going down, what is the end behavior going to be for both of these? Yeah, negative infinity. So we only have to check the biggest power. So let's take a look at this guy right here. Does everybody agree that this is the highest power? Second power? So it's even, isn't it? So if it's even, it's either doing this or it's doing this. Now, look at the coefficient, the sign in front of it. This sign is what? So is it doing this or is it doing this? It's doing this, isn't it? So what's the end behavior going to be on both ends? Negative infinity. So you can kind of sketch it and see. End behavior is negative infinity, isn't it? All right? So we would write that. So we would say this is going to look like this. Okay? It's going to look like that. Because we're looking at y equals negative x squared. We don't care about the rest of it, guys. We're only looking at the highest part of it. So the limit of f of x as x approaches negative infinity. Remember, we always just write these to start with. And we're going to fill both of those in as what? Which way is it going if it's doing this? Yeah. Negative infinity. Because of this, correct? All right. So look at what happens if it's odd. What if the highest power is odd? What if the highest power is odd? It's going to look like this. If the coefficient is positive, it looks like this. If the coefficient is negative, it's going to look like this. So can we see what's happening to those? If it looks like this, guys, to the right it's going where? Positive infinity, and to the left it's going negative infinity, isn't it? That's if the power coefficient is positive. If the coefficient is negative, it flips over. And to the right it would be going where? Negative infinity, and to the left it would be going to positive infinity, wouldn't it? So you just have to look at it. So let's look at this guy. X minus 1 cubed. So my function is y equals x cubed, isn't it? Doesn't that cube go there? That's all I need to worry about. I don't even need to worry about this minus 1 part. I just have to look at the highest power. So this is odd, isn't it? Odd and positive. So it's odd and positive. So it's going to look like what? That, isn't it? So then we write our two limits of f of x as x goes to the right. What is this guy doing to the right? This means to the right. So what is it doing to the right? Positive infinity. Okay? So this is going to infinity because this is this end. Now, the limit of f of x as x approaches negative infinity. This, guys, is looking at this end, isn't it? So which way is it going? Negative infinity. So you just look at the lead coefficient and the highest of the highest power, and you decide, is it even and positive, even and negative, even positive, even negative, odd positive, odd negative. That's simple. Okay? So let's look at this guy. What about this guy? It's got a cube. Does anybody want to say this is odd? What do I have to consider? They're sneaky on you sometimes. I've got a cube here, but I've got a what here? Another one, don't I? So we have to consider this whole thing. X cubed times x is what? X to the 4th. So this is even and what? Negative. So even and negative is going to look like what? Isn't it? So even, negative, our sketch would look like this, wouldn't it? Our polynomial would be negative 1/2 x to the 4th, and then we're going to write our limit statements. So what do you think so far? What did you fill in to both of those? Negative infinity and negative infinity. All right. I want you to figure this one out. What is my highest power? What is that going to look like? We're going to have to take this and distribute there, won't we? So what will I write? Yeah, negative 3x to the 5th. So it is what and what? Negative and so sketch that one. What is negative and odd going to look like? And then write your limit statements. Did you make this your sketch? Okay, so write your limit statements. The limit of f of x as x goes to the right. The limit of f of x as x goes to the left. Correct? Okay. So if that is my graph picture, what do I fill in? As f of x goes to the right, what goes here? Good. Negative infinity. As x goes to the left, what goes here? Positive infinity, doesn't it? Negative infinity, positive infinity. Okay, so I think this section is too big for one day. I think if I push you, we could probably get through the last bit, but your brains are going to explode. So, what I want you to do is I want you to do 1 through 3 on your exit ticket. Turn those in, and then I want you to do through problem 12 on your homework. 1 through 3 on your exit ticket, 1 through 12 on your homework. I'll write it right up here. 1 through 3 on your exit ticket, that's the small one, right? And then 1 through 12 on your homework. And we will finish this up next time. Okay? Huh? Oh, you got 2 of them? And just turn your exit ticket in when you're finished. I will put the tray out for you. Right here. How about I put it right here? great way to think of it. She just asked me, she was talking about jump discontinuity, and I love this analogy. She said, is it like the square rectangle thing? You know, a square is always a rectangle, but a rectangle is not always a square, right? So a piecewise function is, a jump discontinuity is always going to happen with a piecewise function, but a piecewise function is not always going to have a jump discontinuity. So you look first at whether it's piecewise or not. If it's not piecewise, then it can't be jumped. And then if it is piecewise, then we check those points and see if it can work. Okay? All right.
We're doing
Yeah, just 1, 2, 3. Start by factoring. And that's what we're going to work on next time as we, I think we're going to do a little factoring review for some of you who think that anybody think their factoring is a little weak? Be honest. Okay, yeah, most everybody in this room. That's fine, we've got a little extra time if we're just going to do 1, 3 next time, finish it up. And we're going to work on some factoring in class and see if we can't get your factoring stronger. Can't hurt anybody. yours back if you borrowed one. Thank you. Yes. Appreciate it. Mark you off my list. Tray. Black tray.
She don't.
Yeah. You'll be all right. You'll be all right. I promise. It will be okay. Black tray. I usually have it sitting up here, but I've got a demo thing sitting up there. Bye guys. Have a great day. Do I take late work? Not typically, no. Why? What's going on? Don't have your homework?
No.
Is there a particularly good reason?
I didn't have time to do it this weekend. I was doing family stuff all weekend, so I wasn't at home. And then I got home late last night, so I couldn't.
Are you in band or?
No, I was still doing family stuff. Not over the weekend, but yesterday.